The purpose of this brief tutorial is to discuss how we write an expression for the refractive index of a conductor, like a metal. So this will teach us how light interacts with the mirror surface coating, for instance. In general, suppose we were to draw a region of space. A region of space, like a piece of glass, can have some bound electrons. So for that, I might draw a nucleus and some electric charge around it, representing our familiar ball of charge around a nucleus. And a bound charge is, if an electric field oscillating to left and right is applied, that bound charge only can move a certain amount. It isn't able to flow within the material. And in glass, that's all we've got. So in glass, we wrote this expression that I'm circling here for the susceptibility of bound electrons, and there was a density term, there were some fundamental constants about electrons, and then there was a resonance frequency, because the electron mass on spring sort of problem has a resonance frequency. Here I'm calling that omega squared naught b for bound. And then we had other terms, and we had a damping term for bound electrons as well, due to the fact that when they shake, they radiate. Now, in principle, there could be other electrons. There could be, I'll draw another electron here, and that's a conduction electron charge, and it's free to move a much greater amount. It can flow within the conductor. So in principle, we could have an exactly parallel term for conducting electrons, where we would have the density of conducting electrons, which in a normal glass would be 0, which is why this term goes away. But then we could have resonance frequencies, we could have damping rates for conduction electrons, and in general, we have to take these two into account. Now, in the case of an unbound electron, you'll notice that if we think of this as a mass on a spring, the K for the spring is 0, and therefore the resonant frequency, omega 0 conducting, which is the square root of K over m, where K is that spring constant, has nothing to do with the wave number, that equals 0. The resonant frequency for this electron mathematically is 0. As a result, this term goes away. And we're left with a denominator which is quite small compared to the typical term here if we consider ourselves in the visible regime, where omega is always going to be less than omega naught. So if we're shining visible light on a metallic mirror, this denominator is always going to be much, much bigger than this denominator. So this term dominates for visible light shining on metals that coat mirrors. So because this denominator is so small, this entire term becomes negligible, and the overall susceptibility of the material is approximately just due to the conducting electrons. This then leads to massive simplification of this expression, and we now have that chi total is equal to, well, we've got this numerator up here, and this has units of frequency squared, because the denominator has units of frequency squared, and susceptibility is dimensionless, it's a ratio. So this numerator must have units of frequency, and we're going to give that a particular name. We're going to call it the plasma frequency squared. We'll talk in class about why this is called the plasma frequency. It's related to the fact that free electrons moving around in space are often called a plasma. And the denominator becomes negative omega. The first term is negative omega times omega. The second term, we've factored out an I, and then the damping rate for conduction electrons. So we have this very simple expression for chi, and remember that once we know chi, in the Lorentz model, we can then get access to the refractive index. Now we have to ask ourselves the question, what's the damping rate and what's the optical frequency? And in the visible range, for reasons we'll discuss in class, mathematically the important thing is that the optical frequency is much greater than the damping frequency for conduction electrons. And the physical statement that's being made here is that the loss of energy mechanism for these guys sloshing back and forth is that these electrons will occasionally slam into nuclei and get scattered around within the metal. And what this is saying is that we're shaking them at such a high rate, they don't tend to ever collide with anything. So we call this the collision-free model limit. So we're not losing energy due to collisions. So then this becomes an even simpler expression, and we have a chi total equals negative plasma frequency over optical frequency squared. And that means that, therefore, the refractive index squared is 1 plus chi. That's the dilute limit formula, the limit where neighbors don't influence each other. And that just becomes 1 minus this plasma frequency over omega squared. And in this case, there's two interesting limits. When omega is greater than the plasma frequency, then this ratio is some number less than 1. When you square it, you got some number less than 1. And in that case, n squared is going to be equal to some number between 1 and 0. So you've got 0 is less than n squared, which is less than 1. And when you've got omega less than the plasma frequency, you've got a situation where this ratio is a number greater than 1, and you've got 1 minus that ratio squared. So now you've got that n squared is less than 0. So these are two interesting physical situations which we will talk about. Neither of those are properties of refractive index that we encounter in ordinary materials in the visible regime.